All right, good. Hey, listen, we started right before we did this. There was a question on your quiz that was just like this. It said, figure out the six trig functions. So these are the six trig functions. A little bit better defined. Defined in the sense that in reality we should have done over hypotenuse in each one we did with the unit circle, except for the fact that our hypotenuse was 1, an identity property, which means it didn't matter. Now we are going to bring it into consideration. So go ahead and just write down the 6. You don't need to write down like the whole word. You don't have to write down opposite. You could write over H. I went ahead and put the acronym up there, the SOHCAHTOA, because it's so convenient for us. Now, the ones that you're not so familiar with is cosecant, which is hypotenuse over opposite. So is secant, which is hypotenuse over adjacent, and cotangent, which is adjacent over opposite. The biggest thing we're going to draw from this is that now we're going to deal with triangles that are no longer in the unit circle. So the hypotenuse is going to be important. We are going to take in consideration, we are going to use it in order to solve some of these triangles. Now, most of y'all should have finished writing this down. We're going to get into an example, so bring some excitement right away, just because we're going to be finding the exact 6 values of this triangle. So we have, go ahead and write down the example. Write down that we're going to be dealing with the triangle, which is, we're going to do similar to what we did in the quiz, just with the fact that now we're going to have hypotenuse added in. We have 2 sides of the triangle, 2 and 3. So draw that, and also go ahead and please draw a triangle. Now, because we're missing one of the sides, we actually cannot yet solve or come up with all 6 trig functions. We do have the hypotenuse, which is the c value. C is equal to 3, so that's lovely. B is equal to 2, but we need to create the opportunity to find out A. A is the unknown. A needs to be done because when I deal with cosine, tangent, secant, and cotangent, it requires the use of adjacent. If I set this as my reference angle, the theta here, then the adjacent, it actually involves 4 trig functions. Now, anytime we have a right triangle, though, we have the ability to use Pythagorean to solve for it. Yeah, so we're going to apply Pythagorean Theorem, a squared plus 2 squared is equal to 3 squared, and solve for a. From here, it becomes a pretty easy process because all we do is we isolate A by subtracting 2 squared. I'm going to make them the whole number. 3 squared is 9 minus 2 squared, which will be 4. So from here, we will be able to now get a proven, I mean by proven is that you use it quite extensively to actually get an answer for that side. Yeah, well, it's going to be 5. So we're led to find out that when we take the square root of both sides, we discovered that A is really the square root of 5. So with this now, I'm able to solve for all 6 trig. And it's fairly simple just because we've done similar process. We'll start with sine, our first trig one, and we'll apply, or state, better put, the sides, opposite over hypotenuse. So the opposite side in this case from the reference angle that we marked will be 2, and hypotenuse would be 3. So that's lovely because I got the first trig. Second trig function is going to involve cosine of the angle, and it's going to involve the one we discovered, the A value, the adjacent side. And in this case, it's going to be the square root of 5 over 3. So that's lovely as well. And let's do the last one, the tangent. The third in, not the last, but the third in the SOHCAHTOA part, the third being the tangent of the angle, means we're going to have opposite over adjacent, which means that we're going to have, from this angle, the opposite would be 2, the adjacent would be the square root of 5. Now when I write this down, there should be lights going off on the top of your head, stating that something else needs to be done, which being the square root, being in the denominator, yeah, we can't leave it. So we're going to rationalize that by doing the multiplying square root of 5 top and bottom. So when we multiply square root on top 5, top and bottom, we're left with this answer, which is 2 square root of 5 over 5. So it's lovely. I have 3 of the trigs. I need to find the other 3, the reciprocal ones. One of the nice features that is beneficial to you is that the reciprocal also just reciprocates the actual values. What I mean is that cosecant, yeah, is just flipped. Cosecant of the angle is now hypotenuse over opposite, which means that instead of having 2 over 3, we have 3 over 2. Secant of this angle follows the same idea, hypotenuse over adjacent. So with this one, I'm going to get 3 over the square root of 5, and the same light should be going off on top of your head saying, hey, we need to change this. We got to rationalize the denominator. So we're going to do the same thing we did with the tan function. Multiply square root of 5 top and bottom. We'll get a slightly different answer, because when we do this one, when I multiply the square root of 5 top and bottom, I'm actually going to end up with the result of 3 square root of 5 over 5. So, so far, 5 trig functions down. Pretty good. One left, cotangent. Being the reciprocal of the tangent function means that with the last function, which is number 6, my cotangent one, I'll take the angle and I'll go ahead and I'll do the adjacent or opposite, and I'll find out that this is really the square root of 5 over 2. Actually easier than the tangent function because no rationalization required. Everything is set in. So we have this. Now there is something to do with right angles that I want to discuss. It only happens in right angles. That we have these angles that are in here. Now, do y'all remember that in every triangle there's 180 degrees of all the angles, the measurement in the inside of it needs to be added up to 180? That still holds true. But with right angles, there's something special. If I call this alpha and this beta, the only reason I'm calling this one alpha is because the opposite of A and beta opposite of B. There's something that occurs. Remember, this one takes up already 90 degrees, which means that if it being 180, the other 2 angles need to occupy the 90 degrees. They are both acute, meaning that there was something y'all learned in geometry that they used to call complementary angle theorem. The complementary angle theorem meant that if you have two acute angles, they both are going to add up to 90 degrees. So this is a special property. Now, it's exciting because these properties, these angles, being that they add up 90 degrees this way, actually has us the ability to prove some other things that they have in common. But first, let's write about complementary angles. Write this down. Complementary angles, being that we call the opposite I, we call that one alpha. This alpha and this beta notation is just for standard notations. That means anytime you label your triangle, when you label it a side A, I know that the opposite is going to be alpha. Same way when you label a side B, then the opposite would be beta. But then we have the definition of two acute angles. That means the sum of complementary. And if you have a right triangle, we also end up with this, we're actually guaranteed this thing called cofunctions. And we'll get into that. Let's see where everybody's in track. All right, good. Okay, now let's go ahead and define what is a cofunction is. Now, it's interesting because one of the things that we get guaranteed that we could say safely is that there is an equality that happens with these. Now, this is what occurs. When y'all look at this triangle, you see how it's we have these sides labeled? Okay, down, supposing, before you start writing these stuff down, if I wanted to figure out the sine of beta, then you'd be saying, I'm going to stand about, go ahead and take the opposite, which is the B, and divide it by the hypotenuse, which is the C, right? So I'm going to go ahead and actually do this. I'll get whatever value comes from B and C. So that's lovely. But let's say I take the alpha, the cosine of alpha. Okay, the cosine of alpha, it's adjacent, isn't it, from this angle? So adjacent is B over the hypotenuse, which is C. Now look at this. Do you all see that it's the same values? It's B and C, that it's over. Both the and it takes a little bit. The sine of beta is both B and C, and so is the cosine of alpha is B and C. Which means that if they both equal the same value, what does that mean? They're equal. Yeah, they equal. So that's the reason why y'all see that written on top. Sine of beta is equal to cosine of alpha, which means something simple. Let's put some numbers in it, make it a little bit more defined, a little bit more concrete. Let's call this, well, let's call this 72 degrees, which means that this over here is 18, right? Okay, so I can tell you with confidence, and I can prove it to you, that the sine of 72 degrees is equal to the cosine of 18 degrees. So it's safe for me to say that now just because it's been proven. Now just go ahead and write this down though. Write down the cofunctions because you have to know those. You have to know these cofunctions. All right, good. So let's actually get into another, we're going to get to a delightful example, which is going to be the, actually just doing this cotangent function. So the cofunction. Really all it is this. Well, not this, right over here. All right, so we have a complementary angle theorem means this. We've shown that the sine of one is the equality of the other as far as the, if you're looking at, like in this case, these two angles, the sine of 20 degrees is the same thing as the cosine of 70 degrees. What I like for you, and the reason, and the way you always could do this, if let's say this, one of these was unknown, like let's say that one was unknown for some reason, you would take 90, subtract 20, and you'll get the 70, and that's how you know that this is 70. So do something similar with this bottom one. I'm going to call somebody randomly. Try now what the answer would be for the cotangent. I'm looking for the cofunction. Some more excitement in here. Let's see. Thrill. Two. Alex. Is he awake? Pretty sure he's been asleep this whole time. Oh no, he's not good. Alex. That's fair. Alex, you were called on. Right. You might have been asleep, so this is the only time I'll bypass you. 15. Alright, let's see, who's 15? You're the closest one, Spencer. No, I know it's a different, but it's a seating as far as the numbering, still the same spot. So don't worry, I know you know the answer to this one. So don't worry. I know, but what exactly? If it's the tan? Yeah, remember the function, the cotangent is tan, so it would have been the tan of 53 degrees. Oh, yeah. It's just the evaluation of this one. I'm sorry. Let me change this. Make sure it's 53 degrees. And all it was done is subtraction. Yeah, 90 minus 37 ends up 83. You just find the correct trig function, which is a cofunction that derives the same value. Once you know that, then we have a simple answer being this. All right, lovely. Okay, listen, let's have you all do now this next one. Write this down. We're going to find the exact values to both of these. And then just use the complementary angle theorem to find exact value. Without the use of a calculator. Okay, hey, listen, let's go ahead and actually solve this. Now, one of the things that we're going to have is that we're going to use you have to use complementary angles in order to solve this. Now, we have an option. There's one thing that we do know, and we know that we have the opportunity to use either cosine or sine, and the reason being is this. Like, let's say I start with the sine of 38 degrees. One of the, if I'm asked to find the cofunction of this one, it's going to be cosine. And guess what the value of it is? 52, right? So we have the option now. So we're given the opportunity to either substitute the sine or cosine. Since I started with sine, I'll say I'll substitute it with all these the cosine of 52. Meaning this, do you see what it says sine of 38? That's really cosine of 52 degrees. And you see over here what it says sine of 38? This really is cosine of 52 degrees. Just substitute them, change them. Now, anytime we have a number divided by the same number, it results in an answer of 1. So the division means that I'm going to have 1 plus 1. Which is 2. So for this one, the answer would just be 2. That would be the exact value for that one. Just be 2. So we will have 2 as an answer. We'll do the next cofunction, which will be the now this next one on the right is a little bit more involved, and the reason being is that it's a tan function. Being tan, we could think about it a few ways, and I'll tell you what it is. We could think about it as being a tan function, the trig function. Remember the trig, you could also break this up. Remember tangent is really then cosine. It's really opposite over adjacent. Okay, so you could think about. One of the things that we could do, though, is that probably the easiest way to think about this is this. Okay, if y'all remember that the tangent of theta function, it's in reality the let's see, it's going to be opposite. It's really sine of theta over cosine of theta. Okay, that's one of the identities that you learned back in geometry, that it's either one. So we could have the possibility of either transforming this into this and then finding the value, or remember the cotangent, it's just the reciprocal of it. So the cotangent is going to be the cosine of theta over the sine of theta. Or we could go ahead and actually convert it to this, one of the two. Let's go ahead, and in this case, probably the easiest thing to do that I'm seeing, let's make them both into tangent functions. Now all I'm going to do is that, because remember I have a couple of properties I could play with, I'm going to actually focus in on this one. I'm going to take the opportunity and safely say that for me, the quickest way I see the solution to this, the quickest way to explain to you, is take the cosine of 70 degrees. And we know that that equals the sine of 20, right? So if I have the sine of 20, if that's equal to it, that means I could cross this out and place in, substitute directly the sine of 20 degrees. Yes. Oh yeah, I wrote a couple of options. Okay, I wrote a couple of options actually. I took only one of them. The option I took was this one. I'm going to take this one, and I'm going to use this idea. Okay, I'm going to use that idea because now you see how I have the sine of 20 over the cosine of 20 degrees? I could call that now the tangent of 20 degrees. So the one that I did not use was that one. I have the possibility of using that one too. But I went ahead and did this. So this one was really then the tangent of 20 degrees minus the tangent of 20 degrees, which means that I have the net result of 0. And that's where we'll end today.